Next tonight, a story about astronomy. Despite the failure of the Hubble Space Telescope, the 90s could prove to be astronomy's greatest decade, thanks to the incredible progress being made in the design and construction of earthbound telescopes. Correspondent Jeffrey Kaye of public station KCET Los Angeles has our report.
It's a Friday night on California's Palomar Mountain. Astronomer Don Hamilton is observing stars while listening to his favorite composer, Wagner.
What is the magnitude of this font? Focus, please.
This evening, Hamilton tests out a new piece of equipment of his own design, one which can analyze the chemical composition of light from more than 100 stars at once. Hamilton has come to Palomar for the same reason every astronomer who can comes here. It's the best telescope in the world.
For 50 years, science has moved forward at breakneck pace. But in one field of endeavor, the building of large telescopes, scientists and engineers have been unable to surpass, much less equal, the Hale telescope here at Palomar Mountain in Southern California. It began operations in 1948.
1.5 arc seconds south and 1.5 arc seconds east, please.
What separates Hale from all other telescopes is not its state-of-the-art equipment, but a critical component that was designed in the late 1930s, its 200-inch or 5-meter mirror. The mirror is the key part of any telescope because it collects the light from distant stars and galaxies. The larger the mirror, the more light it can collect, and the better the images. Robert Brucato is the assistant director of Palomar Observatory.
The 200-inch mirror was made from a 20-ton piece of Pyrex, 200 inches in diameter, which then had to be ground and polished to the precise figure that we need to make it into an optical element. The grinding, by the way, removed 5.5 tons of glass to get the concave shape that we need. So the mirror now weighs 14.5 tons. Learning how to make a single piece of glass that big was not easy.
In fact, it was sufficiently challenging and took sufficient creativity to build it that subsequent to that, people were daunted by the thought of building something bigger.
Jerry Nelson is an astronomer at the University of California at Berkeley.
The next generation of telescopes after the Palomar were actually smaller. And so the perception was that we were really pushing at the limits of that geometry, of that approach at the 5-meter level, and scaling it up was not going to be a particularly easy thing to do.
Until quite recently, in fact, building a mirror larger than 200 inches just wasn't possible. The Soviets tried it in the 1970s, constructing a 236-inch mirror, but it weighed 41 tons, 3 times more than Palomar. The result? A mirror too heavy and too thick to be of much use. The mirror's weight caused it to be distorted by the forces of gravity, and its thickness resulted in the glass having different temperatures, ruining the mirror's optical qualities. The failure of the Soviet telescope caused many astronomers to pin their hopes on the Hubble Space Telescope, which was launched in 1990. While Hubble's mirror is half the size of Palomar's, by being in space high above Earth's distorting atmosphere, it was expected to gather light more efficiently and to obtain crisper images than Earth-bound telescopes. But shortly after Hubble's launch, it was discovered that its mirror was flawed. In the wake of the Hubble fiasco, it became clear that for astronomy to move forward, it would have to do so on Earth, and the focus returned to the need to build larger mirrors.
We want more light. The stars are too faint, the galaxies are too faint. We can't get enough light to do what we want to do. So more light helps almost every astronomical program. To get more light, you need more collecting area. More collecting area is just the area of the mirror, and so you want a bigger mirror.
Roughly speaking, the tolerances should be about 10 to the minus 4.
Today, the dream of building a larger mirror is near reality, thanks to new technologies. Several American universities are designing or building telescopes which will surpass Palomar. A key player in all this is Jerry Nelson. In the late 1970s, Nelson was part of a University of California team looking into new methods of building larger telescopes.
People were very skeptical because the plan that I proposed for building a large telescope was very different than other telescopes. I suggested that the primary mirror should be segmented, which was unheard of.
Nelson's idea was to piece his mirror together like a jigsaw puzzle. Each mirror segment is only 6 feet wide and 3 inches thick. Because they are small, the segments are very light, and therefore unaffected by the forces of gravity or changes in temperature. In the past, the idea of mirror segments wasn't tried, because it was difficult to get them to work together closely enough for the precision optics required in astronomy. Nelson solved that problem by placing the mirror segments on a specially designed frame. The frame allows each mirror to be actively controlled by a computer, which ensures perfect alignment.
The primary mirror consists of a mosaic of 36 hexagonal segments. And the task the so-called active control system has to do is to hold those mirrors in the correct position so that mosaic acts as though it's a completely rigid monolithic mirror. To do that, each mirror is controlled in its tip and its tilt and its piston forward and backwards.
In the 1980s, the University of California and the California Institute of Technology joined forces to build Jerry Nelson's telescope. The project received most of its $90 million in funding from the Keck Foundation. The site they chose was Mauna Kea on the island of Hawaii. Mauna Kea, a dormant volcano, is 14,000 feet high, placing the telescope above most of the clouds and turbulence, giving astronomers an unprecedented window into the night skies. Jerry Smith is the Keck Telescope project manager.
We're now building up the mirror. We plan to now build it up to the full 36 segments by about the end of March next year. And while we're building up the mirror, we're testing the telescope optically and testing the control systems. We expect to start doing astronomy hopefully next summer.
When it's complete, Keck's mirror will be 400 inches wide, twice as wide as Palomar's, and it will have 4 times the collecting area. Yet it will weigh about the same, 14 tons. Scientists believe this new telescope will be so powerful, it'll be able to see light coming from 12 billion years away, light which is very dim and has taken 12 billion years to journey to Earth. In that respect, Keck will become a time machine, and its astronomers time travelers as they peer back to an era when the galaxies were first forming. Jim Gunn is an astronomer at Princeton University.
The galaxies should be quite bright when they're first forming. And so it may be possible with the Keck and with other large telescopes, not quite so big, to map the whole history of galaxies from the time they're formed, what they were like in the early days when they were forming stars really very precipitously, and basically how they have come to... The galaxies are now in a state where they've mostly run out of fuel. There's 20% or so of the gas left, but most of the matter in them that can be made into stars has been made into stars. And following that history is a very, very interesting thing that I think Keck will say a really great deal about.
In the high-tech quest to build and design huge mirrors for telescopes, Jerry Nelson is not alone. One of his principal rivals is Professor Roger Angel at the University of Arizona in Tucson. Professor Angel builds his mirrors right here, below the stands at the football stadium.
But the haze is really thick.
Angel takes an altogether different approach to the subject. Instead of making a large mirror with small segments, he builds a mirror the old-fashioned way, as one single piece.
It was our assessment when we started this 10 years ago that there would be tremendous value in making a mirror that was both rigid and lightweight, but that the technology to do that simply didn't exist within the industry. And the only way that we knew to get that moving, right, was to experiment ourselves and learn how to do it.
Like Nelson, Angel's background is as an astronomer, not as an optician or engineer. So in designing his mirrors, he brought a fresh approach to the field.
Because people have been building the telescope pretty much the same for 50 years, telescope building was barely considered something that astronomers should know very much about. Right? That was something that if you wanted one, you ordered another one just like the other one.
But Angel's mirrors aren't like anything ever built before. In January, Angel's Mirror Lab will cast a 6.5-meter mirror, which will be 25% larger than Palomar's, but will weigh 5 tons less. What makes Angel's mirrors so light is their unique honeycomb structure. This allows them to be cast with air pockets in them. In fact, 50% of his mirrors are air.
Still got a wall there and a bit over there, isn't it?
Angel's single-lens mirrors, according to Princeton's Jim Gunn, have clear advantages.
It's just so much simpler to support, and so the whole structure, in some sense, is more like classical telescopes. There's just a good deal less to worry about.
Besides building the 6.5-meter mirror, which is for a telescope near Tucson, Angel's Mirror Lab also has several other projects on the drawing boards, including the Columbus project, which calls for 2 8.4-meter mirrors, which will be mounted side by side. Meanwhile, the German company Schott is working on a new technology to cast single-lens mirrors for a European telescope in Chile, which will have 4 8-meter mirrors. Whichever approach turns out to be best, it's certain the 90s will be the most exciting decade ever for astronomy, because the new telescopes coming online are big enough and will produce such quality images that we may be able to see for the first time how this universe we call home began.